Today I'm going to talk a little more about testing capacitors. Now I'll show you a list of some of my other videos that you might want to refer to that'll go into some of this more in depth in a minute. In the back here is an ICO resistance capacitance comparator bridge. The thing that the most important things about this that are interesting are that it for this this video is that it measures capacitance and it also measures leakage. There is a voltage control that goes from 0 to 400 volts that allows you to measure capacitor leakage using this magic eye tube. Now, this particular instrument I restored as part of the Vintage Radio Workbench series. So if you're interested more in that, take a look at that. And if you're interested more in testing capacitors, I'll show you some videos that I made earlier that you might be interested in looking at. But the question you might be asking is, you just in the last episode showed us your method, which is to replace all the paper capacitors. Why do you need to test? And the answer is that new capacitors, and generally I tend to use either these yellow type axial lead or these orange drop capacitors in anything I restore these days. So if you're going to replace all these paper capacitors, why would you want to test them? Well, first let me refer to the difference between the capacitors you see in this first column and those that are in the middle column. These are electrolytic capacitors. You may notice that many of them are marked with plus and minus signs, and the reason is these are polarized. Paper capacitors are not polarized, but there is an interesting characteristic of a paper capacitor because of the fact that it uses a foil, two pieces of foil wrapped up, that is called outside foil. You notice that these are lined up where all of them have a stripe on this end. That is the end that is called the outside foil, and we'll talk more about that in a minute. In fact, I've got a little demonstration for you. We are not primarily going to be talking about testing electrolytics today, mostly about testing paper capacitors. And the main reason for that is when you replace one of these paper capacitors with a polyester, whether it's this axial lead or an orange drop or anything similar, there are two things you want to know. Well, actually three. One is the capacitor the right value? And you can do that on an old, if you want to do that a vintage way, you can do that on an old instrument like this ICO capacitance bridge, because it will balance a bridge at the capacitor value, and it'll show that on here. I won't demonstrate that in today. The second thing that you want to do is determine whether they leak. And there's a DIY capacitor tester that I built out of an old Popular Electronics article some time ago that I'll refer to, but I'll also refer you to the video on that one if you want to know more. So first thing is you want to know if the value is right. Second thing is you want to know that they don't leak at the voltage that you're going to be using them at. And finally, you would like to determine the outside foil end for reasons that we'll talk about when we get there. On the scope, you see a noise pattern, and you'll notice that when I hold my finger near the screen, it picks up noise. There's noise pretty much everywhere in a lab. Fortunately, the lab that I have is fairly well insulated, or isolated, I should say, from a lot of noise, but you're still, the equipment that you have in the lab is going to generate noise. Now, what I'm doing is I'm testing the outside foil of a capacitor. And to do that, I'm going to switch. Notice a small change in the amplitude. Maybe if I come in a little closer, you can see that better. What I'm doing is I am switching the opposite ends of a capacitor that is just connected across the scope input. That's all. There's no, it's just picking up noise from my lab and transmitting it depending on, to the scope, depending on whether I have the leads reversed or not. Now, I'm going to put my finger on the capacitor, and let me show you what I'm doing here. Here is a little box. I'll tell you what's in it in a minute. I'm just putting my finger right here on the capacitor, and what I'm doing here is switching back and forth between these. So let's go back now to the scope. And look at the display. I'll put my finger on the capacitor and then I switch it. Notice that it's higher and lower. Let me turn off some light here. Maybe contrast will be better. More noise, less noise. More noise, less noise. That is what outside foil is all about. Now, don't worry, I'm going to talk more about this in a minute, but basically the whole idea of outside foil is these filmed capacitors, or I should say capacitors that have a metal, two wrapped metal plates. There is an orientation, and it does matter. It's not because the polarity is different. It's because, in other words, these capacitors are not polarized. But when you replace them with these polyesters, you can reduce the noise pickup in your in whatever you're repairing. It could be a radio, could be a tube amp, guitar amp, anything of that sort. You can reduce the noise if you orient the capacitor in the way that it was originally oriented. So in other words, if the capacitor you took out had the outside foil to the left, then you first have to determine, well, which of these two leads on this capacitor is the outside foil. And then, let's suppose it's this lead. Then you need to put it in the circuit with that lead on the same side, connected to the same circuit point. So we'll talk some more about that. Here is a little bit closer view of the box that I built up. And the purpose of the box is to basically allow me to connect the one end of the capacitor, I'll call it the red end, to a jack at the back that then goes to the oscilloscope. That's the red jack. The black jack, of course, is the ground, but it also allows me, that's with the switch in this position, but it also allows me to switch to this position, which reverses them. In other words, in this position, the red is connected to the black, and the black is connected to the red. It's a simple crossbar. I'll show you the circuit drawn schematically in just a second. So what are we trying to determine? Well, we're trying to determine which is the outside foil. In this capacitor, it's marked. But if we put this capacitor in, it's not marked. Now, I have marked it, this one, with an outside foil. And so I'm just going to replace this capacitor . And now let's go back up to the scope. And I'm going to switch between one and the other. Notice that in this position, there's more noise than in that position. So let's look at what we have there. This is the crossed position. And this is the lowest noise position. When I go to this position, the paralleled position, you get more noise on the scope than you do when you have it crossed. What does that mean? Well, it means that when this terminal is connected to ground, this capacitor picks up less noise from the environment. So that is the end that we want to call the outside foil. Now, whether it actually is the outside foil doesn't matter. Remember, all we're trying to do here is determine, is there an orientation for this capacitor that reduces noise pickup? And the answer is yes, there is. And that orientation is with this end connected to ground, in other words, with this in the reverse position. If we switch the other position, in other words, if we connect this end to ground in a circuit, this capacitor will pick up more noise than if we connect this end. That's all this is about. Maybe another way to look at it is this. This is simply a capacitor formed from a piece of foil, a dielectric material or an insulator, and another piece of foil, and then rolled up. One of these leads is connected to this piece of foil. The other lead is connected to this piece of foil. The piece of foil that winds up on the outside of the capacitor, in other words, this one, is what we are calling the outside foil, and the lead that is connected to that piece of foil is what we call the outside foil. So, here is a little bit of a synopsis of what outside foil is all about. First, what is it? Well, we've explained it. It is basically, what we really mean is the side of an unpolarized capacitor that should be connected to ground or to a low impedance point to reduce noise pickup. Why do we care? Well, let's look at circuits. Remember that a capacitor is just two plates separated by an insulator. One example of a capacitor is a coaxial cable, where there's a center conductor and an outside shield. It's called a shield because the outside shields the inside. Obviously, we want to connect the shield to ground and use the center conductor for the signal. We don't want to connect the center conductor to ground because then this entire outside area would be picking up noise and coupling it into the circuit. Now, let's talk about tube circuits and why they matter more than transistor circuits. A tube circuit, and here we are showing a coupling capacitor, that is, coupling from the output of this tube, the plate, to the input of the next stage, the grid, and bypass capacitors, that is, bypassing a point to ground for the AC signal. In other words, removing as much of the AC signal from this pin as we can. Whether it's a bypass capacitor or a coupling capacitor, we would like to connect the outside foil end of the capacitor to the lowest impedance point in the circuit. Now, in a case like this, the high impedance point is the grid, so you would connect the outside foil to the plate end. In the case here, it's even easier to understand because the ground is always assumed to be the lowest impedance point in the circuit. So you connect the outside foil end to the ground. In other words, the bottom of the capacitor should be the outside foil. Well, why doesn't that matter in transistor circuits? Well, it's a question of impedance. In transistor circuits, both the input and output impedance of a transistor, no matter how it is configured, because it's a current-operated device, its impedance is low. So, the pickup of a capacitor like this, or this, in a transistor circuit is relatively minor. And even if it does pick up some, because it's connected to a low impedance device, it doesn't matter as much. That's why that this outside foil tends to be an issue more with tube circuits than it is with transistor circuits. But I will point out that a MOSFET is very much like a tube. In other words, it has a high input impedance. So you definitely do not want to connect the outside foil to the gate of a MOSFET. Instead, you want to connect the outside foil to either the drain or the source. Now, earlier I pointed out that there is a coaxial cable that is basically just a capacitor through which you flow a signal current. Well, one thing you could do with a capacitor is you could actually shield the entire capacitor. What I mean by that is, using this as an example, you could wrap, here we have two leads, you could wrap this capacitor in a shield, in a piece of metal. That would then make it a three-terminal device. You would have the left end, the right end, and the shield. That's what's depicted here. This is the left end, right end, and shield. Now they actually make capacitors like this, and you can actually make them yourself if you want to, and they're often used in sensitive circuits. A lot of audiophiles like to use these in particularly the input stages of their amplifiers, because it does reduce the noise. This is a much more costly way to do it, but nonetheless it does work. Now let me talk briefly about the switch box that I was using for the outside foil measurement. This is all it is, and you may want to pause the video at this point. When the switch is in this position, the red connects straight through to the red and the black connects straight through to the black. The black is also connected to the case, to the metal case. When the switch is thrown to the other position, the red is connected to the black and the black is connected to the red. In other words, this is down here, this is down there, so black flows to red, red flows to black. So, the question we ask ourselves is, how can we tell where the outside foil is? Well, one way is the little switch box. But the first method is to look at the capacitor. If you have an older capacitor, a new old stock capacitor, it'll have the outside foil marked, because in the early days capacitors were built entirely for tube circuits, and because it was important in the tube circuits, all the manufacturers would measure and mark the outside foil of their capacitors. The second way is the way we just looked at. Measure the amount of noise that's coupled in. That's what I say is compare the coupling. In other words, compare how much noise is coupled into the circuit with the capacitor in one direction or with the capacitor in the other direction. And that's what that little switch box is doing. Now, for this, you can use any sensitive AC meter. And in a subsequent video, I may try some of these. We've been using an oscilloscope, but that's not all you can use. You can use a millivoltmeter, or you can even use a signal tracer. If you look on YouTube, you'll find a number of people who build or repair tube amps who use the tube amp itself as a signal tracer. What they do is put together a little jack that they can use to hook the capacitor to, and then they plug that jack into their amplifier and turn the volume up. They hold the capacitor in their fingers, inducing 60 hertz into it, and then they turn it the other direction, and they also compare the volume. In one position, the volume will be louder, that is, there will be more hum. That obviously is the position that has the outside foil connected to the input of the amplifier. I'll let you look for those if you wish to. The next thing, though, is the source of the signal. In other words, the source of the noise you're using to compare. Now, you can use 60 hertz pickup. That's what I was using, and I was just using the noise in my lab. You can also use a signal generator to couple signal into this. You can use a square wave generator. One YouTuber, Restore Old Radios, has some recent videos, and you might want to go look at those, where he uses a square wave generator to induce the signal, and then he uses a switching box to switch the two ends, in other words, to compare the coupling. If you're interested in some additional videos that I made that might be of use, here are a few, and I'll set them up so that you can see all of them at one time, and I'll discuss them briefly. You might want to pause the video if you want to write any of these down. My numbers 41, 42, and 43, they'll have a TTT in front of them for Tom Tech Test, but TTT41, 42, and 43 are about restoring a Westinghouse AM/FM radio, and I talk about quite a few of the same techniques that I talk about in this video. If you want to see a slightly more complicated, well, actually quite a bit more complicated radio, you might look at numbers 74 through 87, a few in here that are not part of this series, that are the SX62A. That's a Helicrafters, a very fancy tube radio of the period that I restored. In fact, I restored a pair of them in those videos. In my number 129, 130, and 131, I talk about testing capacitors in more detail. In 134, I talk about capacitor testers, things like that box that you saw earlier by ICO. And then in 135, I talk about the DIY capacitor tester. That is the device that I showed earlier that looks like this. And if you're interested in a relatively low-cost leakage tester, you might want to look at that one. My numbers 187, 189, and 193 are about a vintage radio workbench where I restored some vintage radio test equipment. And then in 239, I talked about vintage capacitors. Now in this video, I'm primarily talking about electrolytic capacitors, vintage electrolytics. Modern electrolytics are not made the same way that vintage electrolytics were made. So if you're interested, you might want to go back and look at that. Okay, well, that's enough for this video, but I would like to tell you where we're going. The next thing we're going to do is we're going to actually use we're actually going to replace the capacitors in that radio, that new radio, or new vintage radio that we are using as our model. To do that, I'm going to be doing two things. I'm going to be testing the capacitors for value and leakage, and then I'm also going to be determining which end is the outside foil so that I can replace all the paper capacitors in that radio. At some point, we will get we will also check the filter capacitors for shorts. Now that's a simple ohm meter check, and that's all in the next video. After that, we're going to start wiring up the new line cord and putting in a proper fuse so that we can start to bring up power and measure some voltages. So that's where we're going. Please stay tuned. I hope you've enjoyed this video and perhaps learned something from it. But in any case, look for another one. And in the meantime, have a nice day.